Thank you very much for the invitation and the introduction. So today I will talk about the residual categories of quadratic surface bundles. And then so I will first tell you what is a residual category. And to talk about that, I will first tell you what is a semi-orthogonal decomposition. So here, so whenever you have a triangulated category, you can talk about whether it has a semi-orthogonal decomposition by some full triangulated subcategories. And if it does, this is usually the notation that we would use. So to have such a decomposition, it means two conditions. So first, the condition tells you that these subcategories are semi-orthogonal. It means that there will be no maps between them in one direction. So here, this says that the hum from every object in AJ to every object in AI will be 0 whenever J is bigger than I. So this means that when you consider the maps from the objects on the right to the objects on the left, then the hum is always 0, but you could have morphism from the left to the right. So it's not a completely orthogonal decomposition. And the other thing is that these subcategories should generate the whole category. In a more precise way, it means that whenever you have an object, so in this triangulated category, then you should have a functorial filtration of length n, so that the cone of each map comes from an object in this component AI. So in a way, the semi-orthogonal decomposition is dividing this big triangulated category up into smaller pieces, into easier study pieces. So in this talk, we'll mostly deal with derived categories. And then so there are two types of derived categories we'll encounter, so we'll make the following convention. So when you have a scheme X, I will use the notation dbx to represent the bounded derived category of coherent sheaths on X. So this category, the objects are just bounded complexes of coherent sheaths on X. And then two complexes are isomorphic if their cohomologies are the same. So that's called the quasi-isomorphism. And then the other case is that if you have an algebra, then I will use the notation dBr to represent the bounded derived category of finitely generated right modules over R. So when your algebra is commutative, then this is also equivalent to the bounded derived category of a spec R affine scheme corresponding to it. But usually, the algebra that will appear in this talk will be non-commutative. And then, so now we can define what is a residual category. This is something that you can do for a family of Fano varieties. So here, when I say Fano varieties, I only require the anti-canonical divisor is ample, so it could be singular. So whenever you have a flat family of Fano varieties that is of index n, which means that the relative anti-canonical divisor is O of n, then inside of this bounded derived category, you will have some trivial pieces. So you will have the pullback of dB of the base, tensor of 1, up to fullback of dbs tensor of n as components. So this collection right here, it will satisfy the semi-orthogonal condition, sorry, over here. So it will be part of the decomposition. Then the residual category is just what is remained inside of a dbx. It's called the orthogonal complement of this collection. So more concretely, this will consist objects inside of dbx such that there's no hum from all these pieces where I between 1 to n to the subject. So now they will generate the whole category, gives us a semi-orthogonal decomposition. And then, so this is called the residual category. So usually when you just study like a single funnel threefold or fourfold, you usually would see them to be called the Kuznetsov component. The most famous example would be the qubit fourfold. So now you may wonder, why do we care about residual categories? So you can see right here. So we know that the derived category of a scheme would contain a lot of information about the scheme. But from this decomposition, we can see that you have a lot of like the trivial pieces. So the residual category is a category that lets you to forget about those trivial pieces and then to only focus on what's important, what's left. So you can think this as a refined invariant of the scheme. So if we can have like a nice description of it, then we can understand the scheme in a more efficient way. So in this talk, so as the title suggests, that I will focus on like the quadratic bundles. And then the goal is to try to describe the residual category in a very nice way in this case. So are there any questions before I move on from this part?
There's no questions in the chat for now.
There's no or?
No questions on the chat.
Okay, so before we talk about like the families of quadrics, let's first look at the like a single quadric hypersurface, and then to get a sense of what you should expect for the residual category. So to make things simple, let's just assume now the base field is algebraic closed and the characteristic 0. And then let Q be a quadric hypersurface of dimension n over the base field. So, so one of the first examples of semi-orthogonal decompositions are given by Kapranov for the smooth quadric hypersurface. So in this case, the residual category depends on the parity of the dimension. So when the dimension n is even, then it will be generated by two objects, which are so-called exceptional. So they would be equivalent to dB of the base field K. So you have like two of them who are completely orthogonal. So this whole thing is equivalent to dB K times K. Or in a geometric term, this is equivalent to the derived category of the disjoint union of 2 points. And then when n is odd, then it's just generated by one exceptional object. So that's equivalent to dBk. So here, all these objects, T1, T2, T, they're the spinor bundles on a smooth quadratic. And so for example, when the dimension is 2, your quadric is just the P1 times P1. Then the spinor bundles are just the line bundles O1, 0 and O0, 1. So next, let's try to see a slightly more complicated case, which is the corank 1 case. So you know that like a quadratic hypersurface, it's defined by a quadratic form or just like a quadratic equation. So that will correspond to a symmetric matrix. So the corank here is just the corank of that matrix. So when it's corank 1, this quadric is a cone over a smooth quadratic hypersurface of dimension 1 less. And then this is singular, and then the only singular point is the vertex, and then it has a nodal singularity. So in this case, again, the residual category depends on the parity of the dimension. So when n is even, it's generated by one object. It's called the spinor sheath. So it's similar to spinor bundle. So, but they're not vector bundles anymore. They're just reflexive sheaths. We can still define them for singular quadrics. And it's not an exception object. So, and in fact, it's equivalent to the derived category of the dual numbers. And then when n is odd, it's slightly more complicated. So this will be equivalent to the Z mod to the equivariant derived category of the dual numbers. And this is also equivalent to the derived category of a quaternion algebra. So in general, actually, we also know the answer by the work of Kuznetsov in characteristic 0, and by Al Bernardara Bologna in over any field. So we have the residual category is always equivalent to the bounded derived category over some algebra. So here, this cliff 0 is the even cliffed algebra of this quadratic hypersurface, and you can always like define it, but it's not so important for the talk. So just you just take it for as a black box. So you just know like it's something non-commutative, and then if the quadratic hypersurface is singular, then it's complicated. So actually, so this result will recover the first two cases. This is because like when your quadric is smooth or corank 1, then the even cliffed algebra would just be the matrix algebra over all these algebras that we have seen here. And then you have the equivalence between them by the Morita equivalence. So now the next question would be, what if you have like a quadric of a higher corank? Can you still have like a nice description as the first two cases? So one of the one of the applications of the main result here is that we can give another description in the case of a corank 2 quadric surface. So in this case, the equation for the quadric would be just xy equals to 0. So then this would be isomorphic to 2 copies of P2 intersecting at a line. So the singular locus is now this common line. And then now the residual category is equivalent to dby. Here y is not a scheme, but a differential graded scheme. But this is not too complicated. So here this OY would be a sheaf of DG algebras. If you write this as a complex, it has only 2 terms. So it has only terms in degree -1 and 0. And the underlying scheme is P1. So this is saying that for this two-term complex, if you take the cohomology at degree 0, and you will get, this is the structure sheaf of P1. So we'll actually come back to this later. Okay. So now, hopefully you have some idea what you should expect. And then, so we'll now move to the families of quadrics. So we'll set to the general setting. So now I will take the base field to be any field, as long as the characteristic is not 2. And then we'll fix S to be the base, where I assume this to be integral Noetherian scheme over K. And then it will take E to be some vector bundle on S and L to be some line bundle on S. So like just like the quadric hypersurface is defined by a quadratic form on vector spaces, for families, the quadratic bundles will be defined by quadratic forms on vector bundles with values taken in line bundles. So here, we say Q from E to L is a line bundle valued quadratic form on S if Q is OS homomorphism of degree 2, such that if you consider the following map BQ from E times E to L, defined by this equation right here, so it takes V comma W to Q of V plus W minus QV minus QW. So we require this to be symmetric bilinear. This is actually the associated symmetric bilinear form. So then Q would be a quadratic form. So over here, we can see that, so BQ would correspond to a map from Sin to L. So it in turns would correspond to a section Sin to Edu tensor L. And then this would also, this would be isomorphic to a section on the projective bundle, where it corresponds to a section for O of 2 tensor the pullback of this line bundle L. So now, if we consider the 0 locus, we will get a quadric bundle. So that's the definition. So of course, when the section is 0, there's nothing interesting. So let's just assume this is non-zero. And then Q is the 0 locus inside of the projective bundle. And then it has a natural map to the base S, and we call this the quadric bundle. In this definition, we don't know that. So in this definition, it's possible that the P is not flat. This is because we only require the form to be non-zero, but it could happen that when you restrict this to a fiber, you get a 0 form. So that's why we have the next notion. So we say that this quadratic form is primitive if, for any point in the base, when we restrict the quadratic form to the fiber, this should be non-zero to make sure that every fiber you get a proper quadric hypersurface. So in this case, this bundle is flat if and only if the form is primitive. So you can rest assured to know that in most cases, the bundle you get is always flat. The reason that I use this definition is that in this work, I will actually try to look at fibers with bad singularity, and in the process, we may encounter a quadric bundle that is not flat. So also the other thing, for preparation is that we need to to control how singular the fibers are. So we'll introduce the degeneration loci for the bundle. So we'll say SL to be the locus in S such that the corank of the fiber is at least L, where L is some natural number. So of course, S0 would contain the whole locus, and S1 would be the locus of singular fibers. And then, but you want to be more precise, so you also have S2 where the fibers have corank at least 2, etc. So then in this family situation, the same references I just mentioned before also tells you what is the residual category. So if your quadratic bundle is flat, then we know this residual category is equivalent to some non-commutative derived category over S. So this is the bounded derived category of coherent sheaths as with some extra structure. So you want this to be derived category to consist of coherent sheaths with right modules over some algebra, Cliff 0. And then this is, again, the even Clifford algebra for this family. And you can also just define it in a similar way. Yeah, so here, the thing is, usually, especially when you have very singular fibers in this family, this Clifford algebra, even Clifford algebra, will be complicated. And then this would be like, this category would be non-commutative, which means it's not equivalent to the derived category of some scheme. So the question or the goal is that when can you have that this residual category is commutative or geometric, which means that it has a form that is equivalent to the derived category of some scheme or the Brouwer-twisted derived category over some scheme. So here Z is some scheme over the base S, and A is some Asman algebra over Z. So like an Asman algebra is just an algebra that italocally is the endomorphism of some vector bundles. Okay. So the first thing is there are some cases that we do know this happen. It's from the same sources. So if your quadratic bundle has only simple degeneration, which means that each fiber has corank at the most 1, which means the fiber is either smooth or it's nodal. So in this case, and then plus, if the relative dimension is even, so the reason that we have this condition is that for quadrics, the behavior always depends on the parity of the dimension, and they're quite different. So if your relative dimension is odd, for the residual category, you wouldn't expect to have a scheme appearing there, but you should expect to have a quotient stack. So this is not something, this is something that I don't want to touch on. I want to focus on the scheme case. So that's why I'm only discussing the even relative dimension case. So under these two situations, we'll have the residual category is equivalent to the twisted derived category on some scheme S tilde, where S tilde is the double cover ramified along this degeneration locus S1. So the locus where the fibers are singular. So recall that in the first part, we discussed the case where S is just a spec of an algebraic closed field. So in that case, so if your Q is smooth, then the double cover would just be the disjoint union of 2 points, as we have seen. And then if your quadric is nodal, then the double cover would just be a spec of the dual numbers, the fat points. So it coincides with what we have seen before. So before I tell you the result, let me first tell you what's the optimal situation that I hope for. So my expectation is that when your quadratic bundle whose relative dimension is even, and if the second degeneration locus is a proper closed subset of S, and then the third degeneration locus is empty, then I would expect the residual category to be geometric. So I have explained why I'm restricting to the even case. Sorry, the even dimensional case. And then I'll also explain in a minute why I'm requiring these two. So these two conditions tells you, so this one tells you that for each fiber, the corank is at most 2. So I'm not allowing two singular fibers. But over here, I'm still allowing some corank 2 fibers, but they can't be the whole, be all the fibers. So over here, so far what I can prove is for the surface case. And then, so here are the main results. So when you have a flat quadratic surface bundle, then this residual category is geometric when in the following two situations. So the first, if the second degeneration locus is a proper closed subset and P has a smooth section. So we all know what is a section of a bundle. Here, the smooth just means that this section would consist of smooth points of the fibers. And then, so in this case, actually, there's no twist. So the residual category is just equivalent to dB of some scheme. And the second case is when the base field is algebraic closed and the characteristic 0. And the total space Q is smooth and the base is a smooth surface. So this is like a very specific case. It's mostly good for applications, as we will see later. So first, some remarks. So the first thing is that in both cases, we don't have the S3 will be empty, so there will be no fibers as corank at least 3. Or it means that the fibers have corank at most 2. So for the second case, this is sort of guaranteed by the total space of the quadric is smooth, so then you can't have too bad degeneration. You can check this directly by calculation. And then in the first case, because we're talking about a quadric surface, so a corank 3 means that it's defined by the equation x squared. So it's completely non-reduced and there's no smooth point on the surface. So which means that you can't have a smooth section. And then the other thing is that, so the second part explains why I'm asking for the condition S3 is empty. So if you have any flat quadric surface bundle such that the S3 is empty, then italocally, you can always find a smooth section. So this means that it's possible to generate the first situation to any flat quadric surface bundle with these two conditions, as I proposed in the expectation. So maybe here another word for why I would require this S2 locus to be not equal to S. So as I have discussed before, I mentioned this example where you have a corank to quadric surface. So in that case, you see the residual category is equivalent to the derived category of a DG scheme, which is not a scheme. So this sort of gives you, maybe convince you why that you would want this to be a proper closed subset. Of course, it's not a definitive answer, but it's like sort of a guidance why you would want to have this condition. Yeah, and then lastly, so for the second situation, the proof is like very geometric. So you actually need to do some birational transformation. That's why sort of have to assume the base field is algebraically closed and characteristic 0. And sadly, it's like very specific to these dimensions and it can't be generalized, but it's good for application. Are there any questions at this point? Okay. So I don't think I will talk like the very specific details of the proofs. Maybe just let me mention the main ideas. So there are two things that are used in this work. The first thing is called the hyperbolic reduction. So just vaguely speaking, so for example, when you have a smooth section, then it means that the associated symmetric matrix for the quadratic form will have something looks like this. So it will be this matrix will have the form like this, where it's the direct sum of two parts, where one part is given by this hyperbolic matrix, and then you have a remaining part. So the hyperbolic reduction just tell you that you would get rid of this part, and then get a new quadratic form, and that's the reduced quadratic form that has a lower dimension. So this is for the smooth section case. So in general, you could have something that's of bigger rank. So then you expect to have a submatrix of this type. And then when you do the reduction, you're just removing this part. Okay. And then the other thing is that for quadric surfaces, the derived category has a very close relation to the relative Hilbert scheme of lines. So we can also make use of this for the argument. So now that I have told you the main results in a vague way. So let me also mention what the precise statement. So you have, so here P is a flat quadric surface bundle, And then the first case gives us the theorem 1, which says that if S2 is not S, and then if you have a smooth section, then the residual category is equivalent to dBq bar, where Q bar is the hyperbolic reduction with respect to the smooth section. And the second case, where base field is algebraically closed, characteristic is 0, the total space is a smooth fourfold, the base is a smooth surface, then the residual category is equivalent to a twisted derived category over some scheme S plus. So here, is something constructed out of the double cover. So this is the S tilde, as we mentioned before, is a double cover over S, ramified along S1, which since S is a smooth surface, S1 would be a curve. So here, the curve could be singular, so it could have nodal singularity. And then the singular locus is actually given by S2. So when you take the double cover ramified along S1, the S2 here would be a nodal surface where the singular locus is this S2 embedded inside the double cover. So now this S plus here would just be the resolution of this nodal surface. And then you can just resolve the singularity by taking the blow up. And then, so one thing maybe I should emphasize right here is that, so this S plus has a natural map to the base S. And then if you look at the fibers over this locus S2, then you would just have their P1s. And away from S2, you get it's a double cover. Okay. And then so see here, A plus is just some azimuth algebra that gives you the Brouwer twist. Maybe one more thing is that, so usually when you talk about quadric bundles, then you will have the question of rationality. So here, this A plus give you a Brouwer class on S plus, and then this is trivial if and only if your bundle has a rational section. Okay. So now with these two theorems, I can show you the computation that gives you the description of the derived category of the Korank 2 quadric surface. I think that like this is like an interesting example. So the way I do this is I will find a very simple family of quadric surface bundle that has a Korank 2 fiber and do base change. So here we consider Q to be defined by xy plus tzw equals to 0, where xyzw are the variables of P3, and then t is a variable of A1. So if you write this in terms of a matrix, so you will have the xy, the part gives us this hyperbolic matrix, and then tzw gives us this matrix right here. So you consider the natural map from Q to A1, you have a family of quadrics. So when T is non-zero, then you will have a smooth quadric surface. And when T is 0, then you will have a Korank 2 fiber. And then we call this Q0. And then here, so we have a smooth section, actually have two of them. Either you take the section given by YZW 0 or XZW 0. And then in this case, so you can take either of them. For both of them, when you do the hyperbolic reduction, you will get the same reduced quadratic form, which is just by eliminating this hyperbolic part. And then get Q bar is given by the equation TZW equals to 0 as a subscheme of P1 times A1. So actually here, this is again a quadratic bundle over A1, and you can see away from 0, it's a double cover, so it's a quadratic bundle of relative dimension 0, and over 0, you get the fibers P1. So this is non-flat quadratic bundle that I said that would appear. And then, so now the theorem 1 will tell us that the residual category is equivalent to dB Q bar. And then, so for derived categories or triangulated categories, so we have a base change theory. So this tells us that the residual category of this fiber Q0 is equivalent to the derived category of the base change, but now we have to do the derived fiber product. Oh, sorry. So it should be equivalent to this scheme. So let's call this to be Y. And then, so in order to describe this scheme, we have to replace this point by an isomorphic DG scheme that is flat over the base. So instead of writing this as the point, the sheath, we write this as A1, and then a two-term complex from OA1 to OA1 with the map T. And now the scheme is equivalent to this fiber product. And then this is equivalent to the scheme, which is Q bar, and the two-term complex is given by OQ bar to OQ bar with the map T. And now it's easy to compute that the cohomology at degree 0, which would be the subscheme of P1 times A1 quotient by the ideal TZW and T, which just give you the structure sheaf of P1. But also you see that in the -1 degree, the cohomology is non-zero, so it's a DG scheme, not a scheme. Okay. So I guess now maybe I would jump to the applications for the theorems. Let's see. So the two theorems I mentioned, you can apply to 3 examples. 2 are like reproofs of previous examples. So maybe let me first mention the new example, which is the complete intersection of quadrics. So in terms of the derived categories, the quadratic bundles and then complete intersections are very closely related. So whenever you have a result for the quadratic bundle, then you will have some applications for the complete intersection. So here, let's take X to be the smooth complete intersection of the 3 quadrics, where these quadrics are quadrics inside of P2m plus 3. So this means that the dimension of X is 2m. So here you have these three quadrics that gives you the complete intersection. So they also give you a P2 family of quadrics. So the net of quadrics will give you a flat quadratic bundle of relative dimension 2m plus 2. So now we can study this quadratic bundle. The thing is that the homological projective duality created by Kuznetsov tells you that the residual categories for X and for Q they're equivalent. So you can change the study of the residual category for this Fanol's complete intersection to the residual category of this quadratic bundle. And then, so one of the things that you can get is that when M is at most of 5, then the residual category is a twisted derived category. On some scheme I call S2M, this is just the resolution of double cover over the base P2, where it's ramified along the degeneration locus. And in this specific case, it's just a nodal curve, a degree, 2m plus 4. And when m is at least 3, the corresponding quadratic bundle always has a section, and that's why you will have the complete intersection is always smooth. And then when m is 2, and then when the Breuer class vanish, then you will have the smooth complete intersection is rational as well. So the idea for this proposition is that, as I mentioned, so for the smooth complete intersection, we can consider the net of quadrics to get this family of quadrics of relative dimension 2m plus 2. Since our result is only for quadric surfaces, so we have to make some reduction before we can apply the main results. So we do this by the hyperbolic reduction I mentioned before. So the thing is that when m is at most of 5, then you can always find a Pn minus 1 inside of this complete intersection. So now this projective space Pn minus 1, since it's contained in all 3 quadrics, so it will contain in every fiber of this quadrics bundle. So now you have like a trivial family, and they will correspond to something that you can apply the hyperbolic reduction. So this is like the higher version that I mentioned before. So now you can reduce to a quadratic bundle whose relative dimension is 2. And then here your base is a smooth surface P2. And then when X is smooth, then this total space Q bar here is also smooth. Now we can apply the second theorem to get the residual category, which is a twisted derived category. And then, so this is the description that we have seen before. You do the resolution for the double cover. Okay, so is it like a 15 minutes or 1 hour? Should I stop or?
10 minutes or like.
Okay.
Minutes.
Okay. So maybe since I still have a few minutes, I will mention another example that might seem more familiar to you, which is a famous example of cubic fourfold containing a plane. So for the cubic fourfold containing a plane, the residual category, or I think in this case it's usually called the Kuznetsov component, has been described. So first in the generic case by Kuznetsov, and then in non-generic case by Machete. But with the result of the paper, I can also give like a different proof. So here X is a smooth cubic fourfold inside of P5 containing a plane. And then we can consider the projection from the plane, which will get a rational map from X to P2. And then when you try to resolve the indeterminacy, you will have a map here, a map F, which is the blow up of X along the plane, and another map to P2. So here G, the map G would be a flat quadric surface bundle. And in a generic case, then this bundle has simple degeneration. But in general, you could have some finite number of fibers that has corank too. So in this case, then we would need to apply the theorem 2. So like by the blow-up formula for the derived categories and by some mutations, so we know that the the Kuznetsov component of the cubic fourfold is equivalent to the residual category of Y. And then again, theorem 2 tells you that it's equivalent to, I think I should, I forgot to put the Brouwer twist here. So it's a twisted derived category over the resolution of a double cover, and in this case, it's a smooth K3 surface. So this is something that you would expect. I think I will stop here. Thank you for listening.